As I told you, we'll begin with some review part of the application of lens maker's formula, because that was the last thing we had seen before we got into optical instruments last time. So let's look at quick review and examples. From lens maker's formula. So as you will remember, lens maker's formula was basically an application of the concept of refraction at a spherical surface. Where we saw the derivation of this earlier, that if we have either a concave or convex interface between one medium which has refractive index, let's say mu2, and another medium which has refractive index mu1, then the position of the image formation, this is the center of curvature, this is the so-called pole, and we have an object like this, then due to the bending of light by refraction, let's say it bends like this and forms an image over here. So this situation gives us this formula that mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r. So this was the basic formula which was derived from Snell's law, using the fact that mu sine theta is mu1 sine theta 1 is equal to mu2 sine theta 2, that kind of Snell's law from Snell's law application. Here of course everything u, v and r was substituted with sign convention. Okay. And then we saw the application of this for the thin lenses back to back twice. So for thin lenses we saw that you have a situation where there is refraction happening once from air into glass through this surface which has R1, and then from glass back into air through this surface which has radius R2. So you have those back-to-back formulae that if light is incident parallel to the principal axis like this, let's say, so you have some image, let's say I1, that becomes the object for the second refraction, and the final image becomes, let's say, I2 over here, which is the final image. The first one, let's say, is I1. So for the first refraction, we had the formula that the refractive index of glass divided by V1, let's say, minus refractive index of air divided by U, which will be infinity for when we put the final image position as focal length. Okay. That is equal to refractive index of glass minus refractive index of air divided by R1. And then for the second refraction, what happens is the object is that I1, the image of the first one. So U actually becomes V1. And because it's happening from glass to air, index of glass divided by U, which is V1, is equal to refractive index of air minus glass divided by R2. Here again, if we have substituted U as infinity in equation 1, then V over here becomes focal length. So solving this equation and this equation, we got what is called the lens maker's formula. That is that 1 upon focal length of a lens is refractive index of glass with respect to air minus 1 into 1 by R1 minus 1 by R2. Okay. So this was the formula that is used to calculate the focal length with proper sign convention given the radii and given the refractive index. So here of course remember R1 and R2 are substituted with sign, with their Cartesian or algebraic sign, and focal length of lens also comes with sign. Okay. So let's look at some examples of the application of this today. Start with that. Okay. So let's start with that very common situation that we have. A concave or convex lens. which has radii 45 centimeters and 60 centimeters, and refractive index of glass is 1.5. This is for glass with respect to air. So we have to first of all find its focal length when in air or vacuum. And secondly, if this lens is placed under water and a point object is placed at a distance of 90 centimeters from its pole on the principal axis. Find the position of the image. So let's just work this question out quickly. Yeah, I'm seeing that I've already got some answers. Jatin, you have to check your calculation once more. Be very careful of substituting the signs properly for R1 and R2. Okay, before I forget, one more part of this thing is lens maker's formula, and then of course we also had the lens formula that 1 by V minus 1 by E is equal to 1 by F, and magnification is equal to V by E. So these are the lens formula. That will also be partly used in this question. Yes, Aditya, your answer is correct. Oh, right. Refractive index of water unit, sorry. So refractive index of water is 4 by 3, standard value. Right. So let us look at this in detail now. So what is happening is if we place this lens in this manner, like we have it in the diagram, and this. So you'll realize it's a combination of two different surfaces which are like this. Okay. So our lens actually consists of just this overlap part, this part over here. You'll understand the first surface has, the concave surface has a larger radius of curvature. There's the so-called second surface or the convex surface has the sharper curvature. So it has the smaller radius of curvature. You have to understand that when light is coming from this side, light is coming this way. With the proper sign convention and everything, we'll be taking this as the first surface, and it should have the larger of the two radius. So it will have the radius of 60 centimeters. And this will be the second surface that the light hits. So it will have the radius, which is the smaller of the two, in this case, 45 centimeters. Okay. So with proper sign convention, R2 will be minus 45. And with proper sign convention, R1 will be minus 60. Because obviously we are taking this side of the pole as a negative quantity and this side of the pole as positive quantity. So that's our sign convention. So with this thing in place now, we will substitute these values to find the focal length, and from that we get the idea about. So in air, the focal length of the lens will be refractive index of the glass with respect to air minus 1. Inverse of the focal length will be this. Okay. So now substitute R1 and R2 with proper sign. So 1.5 minus 1 into 1 by R1, which is minus 60, minus 1 by R2, which is minus 44. So further, now what we can do is 0.5, and we can take 15 common. 1 by 45, so 1 by 3 minus 1 by 4. That will give us 1 by 12. So 1 by 30 into 1 by 12. That is 1 upon 360. So importantly, it's giving us a positive focal length, which means that it's a converging lens. The moment in our sign convention, we are getting the focal length of the lens as positive quantity with light coming from the negative side. The interpretation of this becomes that it is a converging lens, like a convex lens. It's a converging lens of focal length 360 centimeters. Okay, so this light will now tend to bend like this. It will be a very distant image because 360 centimeters is very large in comparison. So I'm drawing a rough kind of diagram here. This somewhere there will be a focal length. Okay, now before I come to the second part, I just want to quickly demonstrate one thing, that any lens, including a concave or convex lens, is always symmetrical from both sides. So that means that if I were to flip this lens, it would make no difference to how it behaves. And what I mean by flipping this lens is, I mean to say, now if I were to place this lens like this, so that the convex side is facing the light coming directly. तो मैं इसको ऐसा रखता हूँ, and I keep light coming from the same direction. It will still behave exactly the same. It will still be exactly a converging lens. It won't behave like a diverging lens or anything different, right? It will behave exactly the same. It will behave like a converging lens of the same focal length. So this time the first surface it is encountering is this one. This is the first surface, which has a radius, which is the tighter of the two, so it's a smaller one, 45 centimeters. So with sign convention, R1 will be plus 45. We use the same sign convention, that this side of the pole is positive, this side of the pole is negative. And the second surface will be this one. So this one will have the larger magnitude of radius, 60 centimeters. So with sign convention, this time R2 will come as plus 60. Okay, so my lens maker's formula will be this, 1 upon R1. So R1 will be substituted as plus 45 minus 1 upon R2 will be plus 60. You can see you get exactly the same. 1.5 minus 1, you can take 2 common. So the conclusion is the same. So this is behaving exactly in the same manner. There's no difference at all. And this is true about all lenses. So it's a real focal point. Real focal point. Right, so this. Yeah, Aditya, so is the image virtual or real underwater? No, I think it will be virtual because the object is at 90 centimeters, which will definitely be between the focal point and pole. For a converging lens, an object between focal point and pole always gives you a virtual image. So let's see. Okay, so let's come to the second part. So in the second part, when we take this lens underwater, this situation, what happens is that the focal length of the lens underwater, let's say the focal length becomes f prime. So it is refractive index of glass with respect to water minus 1 into 1 by R1 minus 1 by R2. Let's say this is my equation 1. Whereas if we compare in air, goes refractive index of glass with respect to air minus 1 into 1 by R1 minus 1 by R2. So now we don't need to do the calculation again. What we can do is just divide equation 2 by equation 1. Just divide this by this. So we get f prime by f. So we're dividing the second one by the first one. Is refractive index of glass with respect to air minus 1 divided by refractive index of glass with respect to water minus 1. And this thing you already know, this we have to find out. So we get the equation f prime upon 360 is equal to, this was 1.5 minus 1. This will become, now refractive index of glass with respect to water will be refractive index of glass with respect to air divided by refractive index of water. This is 3 by 2 or 1.5 and this is 4 by 3 or 1.3. This is 9 by 8. So substitute this over here. So that is 0.5 or 1 by 2 divided by 9 by 8 minus 1 or 1 by 8. This will become 4 times. So the refractive index, the focal length will become 4 times 360 or so that's 14.4 meters. So what happens is in comparison to air, it is not able to bend light so efficiently. So the focal length increases. Obviously, inside a medium which is having greater refractive index than air, the efficiency of bending light will decrease. The angle of deviation for light will decrease. So if it deviates less, that means the focal length has to become at a longer point. So this is what the focal length will become. And now we'll use the formula, the UV formula. Okay. Next, use the UV formula for lens for image. This can be. All right, so this is done now. So let's use the lens makers, the lens formula next. So what is happening that underwater only, we are keeping a point object at a distance of 90 centimeters on the principal axis. So we'll use the formula 1 by V minus 1 by U is equal to 1 by F. Okay. Yeah, so you'll see that we will get this as a negative quantity. common. Or you could have taken 1 by 90 common. This comes out to be minus 15 upon 90 into 16, which will become get this as minus 1 by so V is equal to minus 96. So let's understand in the ray diagram what will be happening is that ray is coming out from this slightly bending like this, but they will still be divergent. They won't be convergent. So the refracted rays will have to be produced back. You have virtual image in there. Okay. So this is that case when the object is between focal point and pole or a converging lens forms a virtual image. Okay, so hope this is clear to all of you. So now one of the things that we should understand clearly from all this is that biconvex lenses plano-convex lens and concavo-convex lens. These are always converging in nature. So they have a real focal point. Unless, of course, you're placing them in a liquid, unless placed in a medium, let's say M, such that the refractive index of glass with respect to M is becoming less than 1. That is, the refractive index of that medium happens to be greater than refractive index of glass. That's a very exceptional case. Okay, unless this thing happens. Okay, this we're talking about in a normal situation where the refractive index of the glass with respect to the medium is greater than 1. So That means that whether we have this type of lens or this type of lens or this type of lens, always rays of light coming from infinity will converge to a real focal point. This can be in all three. Now let's do some analysis for this for various type of situations. Analysis. So the first thing is that if object is at magnitude of u greater than twice of focal length. So let's take an example where focal length is, let us say, 100 centimeters for convex lens, and object is at, let's say, 300 centimeters. So we want to find out about the image. We'll understand this both in terms of formula as well as in terms of ray diagram. So in terms of ray diagram, what will happen is something like this. This is your focal point. So this is your double of focal point. So on this side you have like an image of the focal point. This side you have 2f prime. Now I'm talking about an object which is somewhere over here. 2f se zyada dur hai. So it's somewhere like this over here. So this kind of an object PB. So let us first see what our ray diagram shows. So we'll use that similar kind of principle for ray diagram that we had used for mirrors. We will consider one ray parallel to the principal axis. That will, after reflection, go through the focal point. After refraction, that will go through the focal point. So this is one very easy ray to consider always. And another very easy ray to consider is the ray going to the pole. So it goes undeviated. So let's consider a second ray as the one going to the pole. It goes undeviated. So as you can see, that these rays will meet at this point. So that point object B over here, which is the tip of this extended object, is having the real image at this point. It's having a real, and the whole object will have a real inverted and diminished image like this. Another ray you can consider, which will give you an easy result, is the ray which goes through the focal point. That becomes parallel to the principal axis after refraction. So you will have a ray also like this. Something like this. So any ray through the focal position after refraction will become parallel to the principal axis. And all these type of rays, they will intersect to give you that common image of this. Okay. So what we are learning from the ray diagram is that whenever this happens, our image has this property. We get a real inverted and diminished image. And that image will always be between f and 2f. That is what your ray diagram is showing you. That is what I'll show by calculation also. For example, for this one, I'll show you the calculation below. Calculation will be 1 by v minus 1 by u is equal to 1 by f. This will show you that 1 by v is 1 by 100 plus 1 by 200. So that is v will become equal to plus of 300 by 4. You can see that v is plus 75 centimeters. Okay. So magnification, which is V by U, is plus 75 upon minus 300. That is minus 1 by 4. Sorry. Yeah, minus. Okay. This will be minus. So this will become by 2 minus. Correct. Minus. So this will come out to be this. That is plus 150. Okay. So anyway, it's having a magnification factor of minus half. So it is inverted and half the size. So m equal to minus 0.5 shows you that it is a real diminished and inverted as the diagram goes. Okay. So now this is a generality actually. We are just taking the example of 300, but ये 200 से ज़्यादा होगा. So it is more than 2f. As long as it is more than 200, you will always get this type of image. The image will be between f and 2f, and it will be inverted and diminished and real. Okay. Next up, let us look at situation where the object is at distance between f and 2f. So in this case, you will see you will again get a real inverted, but this time magnified image where v will be greater than 2. This kind of situation. So again, the ray diagram corresponding to this time will be something like this. So now if I consider my object to be somewhere here, this, then most common type of ray to consider is parallel to principal axis, passes through focal point. And next most common type of ray is the one through the pole. You can see that they are meeting quite far away. This also consider another ray going also consider another ray going through the focal point. Become parallel to the principal axis after refraction. I'm just drawing some rough diagrams, so it's not exact. But this will show you the point that we're discussing, that the image is going to be having those properties. It is okay, so then this is A prime, B prime like this. Yeah, we're just doing a bit of review of this part. We will come to combination of lens and mirror. So you can see this, for example, if our U is minus 150 and our focal length was plus 100, we would have got B as plus 300. We would have got magnification as minus 2. So just an inversion of that previous case. Now, what I want to focus more on in the analysis part today is the virtual object situation. Okay. So like this now, you will see the third case of this was something you could have picked up in the previous question actually, that when the object is between focal point, that is F prime, and pole, this always gives us what kind of image? It gives us a virtual image. Between minus infinity and pole. And that virtual image is always upright and magnified. This is the case we saw of that converging lens underwater when we kept the object at 90 centimeters, and the focal length was huge, it was some 1440. It was an expected thing that we were getting a virtual image. So that ray diagram becomes something like this. You can see these two rays are now divergent. They are not convergent, they are divergent. So they have to be produced back. to find the position of the image. This is a very important point. Okay, so whenever this happens, you're getting this. So you should not forget this because otherwise it becomes problematic. This is a very important case for you. Now apply reversibility to this, and you will understand that anytime there's a virtual object, what happens? There will be a this kind of image. There will be a real image between pole and focal point. The case for the virtual object is this, that it will give you a real image between pole and focal point, and that will be upright and diminished. Now you might say, how come real image will be upright? That is because it is a virtual object. So you have to understand this kind of ray diagram. Let us say this is a virtual object. So we have any incident ray which appears to be going through the focal point. So that incident ray would be like this. But what would happen is, after suffering refraction, this will actually become parallel to the principal axis. It will not continue this way. What is aimed, had the lens not been there, this ray would have reached the point B. But the lens will converge it and make this ray parallel to the principal axis. Like this. Okay. And similarly, a ray through the pole will go undeviated. So there's a ray aimed at B passing through the pole. Like this. As you can see, these incident rays, these two rays, which had the lens not been there, it would have given you this object as a point object over here. But the presence of the lens converges them such that that object which was supposed to be B now appears to be over here. So this is that case. So you will always get that case. So any virtual object will give you a real upright and diminished image. Between pole and focal point. So now let us understand this in a situation where there's combination of lenses. Then we'll come to situations where there are divergent lenses also. Okay, so let's see an example question. So we have a combination of two thin lenses. So A and B are identical equiconvex, symmetrical biconvex lenses of focal length 100 centimeters each, kept at a distance d equal to 60 centimeters. Now we have an object like this over here. An extended object kept over here. So we have an object of height 6 millimeter is placed at x equal to 120 centimeters as shown. Find the position and size of the final image after refraction through both the lenses. Let's try this out. Okay, people, so let's solve this one thing at a time. So what is happening is the rays which are coming from here, this will tend to go like this, like this. They are giving us some kind of image over here. This I1 will become the virtual object for B. This is the image for A. That will become the virtual object for B. So first let's find that much position. So for first refraction, lens A and object PQ, let's say. So this is PQ. So 1 by B minus 1 by U is equal to 1 upon F. So B is equal to this. Now this becomes, let's say, P prime Q prime, which becomes the real image. Magnification factor is minus 5 for E, but that also becomes the virtual object for second refraction by lens B. Okay. So this is P prime Q prime, this H prime. So this will become minus 5 times H. So as you can see, this distance now will become how much? It will be 300 minus D, where D we had taken as 60. So 240 centimeters. So these are the rays which are incident on this. So now these will converge and give you a final image somewhere here. Let's say that is P double prime, Q double prime. So that will become the final image. So this we want to find out. This is the second refraction. So for this, we'll have to take U as plus 240 centimeters, virtual object. The focal length as plus 100. So 1 by V minus 1 by U is equal to 1 by F. plus of 7 by plus which one is 540? Yeah, that was 600. Yeah? Oh, my mistake. This was 600. So just make a correction there. This is 600 minus, so this is 540. So we would have to substitute here this as 540. So anyway, so this V will come out to be positive of something like this. Something like this. So you can see that the second refraction produces a magnification of by 540. So let's say that height is h double prime. This magnification into h prime. So this will be about h prime. And h prime was 5 times h. So that will be the size. The size of p double prime, q double prime. This is the final image. Okay. So going back to our diagram, this distance here, this will now come to that 84.375 centimeters. And this final size of this image, p double prime, q double prime, that final size would be that value that you're looking at. So that is approximately 0.78 times h, what that original height is. Okay. So this is how we deal with a situation where there is a virtual object involved. So hope the concept of application of virtual object is clear. this thing. Just give me a moment, people. I'll reshare the screen. There's some error which has software is getting hanged. Just give me a moment. Yeah, so this is how we deal with the situation of virtual object. So the first image for A, which was a real image, becomes a virtual object for B. And every time it's the same formula only, but with the correct sign convention. So now when we look at virtual objects for concave lenses, it's a bit more complicated. So we'll discuss the cases. So analysis for concave lens, which is basically a diverging lens. So this can be biconcave or it can be plano-concave, but never convex or concave. Concave or convex or convex or concave is always converging in nature. You remember that. So here what we have previously seen is that any real object will always give you what kind of an image? It will give you a virtual image. Whether the object is here, this is the virtual focal point. So it might form an image somewhere here, or bring it here, might form an image somewhere here. So this is PQ. So VP prime Q prime. So, or even if you bring the object between the focal point and the cone, like this, even then the image is of this type. Images like this. So any real object is only one type of image: virtual, upright, and diminished image. Okay. Between focal point and cone. So all real objects give only one type of image. Okay. But virtual objects, they now give different type of images. Virtual objects can produce real or virtual images, both. Both are possible. So let's understand with an example. So let's say in this example, we have concave lens of focal length 60 centimeters, and we have incident rays which are, say, converging to a virtual image or virtual object AB like this. We have incident rays. So we have a virtual object, EB at x equal to, in the first case, let's take x as 50 centimeters. In the second case, we'll take x as 90 centimeters. And in the third case, we'll take x as 150 centimeters. Find the position and nature of the image. By nature, again, we mean whether it is real or virtual. So just try this out. Apply the proper sign convention. Remember, the focal length given in the question will never be with sign convention. So it's just the magnitude of the focal length which is going to be, but it's given that it's a concave lens. So we know that it is a diverging lens. So with this example, you will understand in which case the virtual object is virtual image, and in which case the virtual object is the real image. तो tell me 30 सेंटीमीटर के केस में क्या मिल रहा है, रियल इमेज की वर्चुअल इमेज? Very good, Siddharth. That's correct. Okay, so let me solve each of these cases. In first case, x is equal to 50 centimeters. So 1 by v minus 1 by u is equal to 1 upon f. We should have to do it minus 60. So b is equal to plus 60. So magnification factor is plus 2. So in this case, you are seeing what is happening is virtual object. It is giving a magnified upright and real image. But in the other two cases, you get virtual images. Yes, correct. So V is equal to minus 1. This is giving us magnification equal to minus 2. This is showing that it is a virtual inverted magnified image. This is what this is. All right, and finally, third case, we are taking x as 150 centimeters. This case, you will see, will give us a virtual but diminished inverted image. So let's see, 1 by v minus 1 by u is equal to 1 by x. We are getting v as minus 2. It means we are getting the magnification factor as minus 2 by 2. You can see that this is giving us a virtual but diminished inverted image. That is what this equation means. That's why I said that both cases of virtual object giving virtual image and virtual object giving real image are possible. But whenever it will be real, actually it will be magnified. Whereas whenever it will be virtual, it can be both magnified and diminished. You have to take negative focal length because it's a diverging lens. You can see given to us that the lens is like this. So the focal point is this ray, for example, parallel to the principal axis. It will go like this after refraction. That is why, for example, if this is real, this is going undeviated. Can give you an image here also. The ray diagram I showed you above, it is corresponding to more something like this, a virtual inverted image. Okay, so let me demonstrate one of the three cases with a diagram to understand this in perspective. So let's take the third case. So this was the virtual focal point, which was at 60 centimeters behind. This is 2F. Okay, so this is the image of the focal point here. This is. In the third case, our virtual object was somewhere here because it was at x equal to 150, whereas the focal length magnitude was 60 centimeters. So something like this. So PB is somewhere over here. So why will we get a virtual image which is inverted but diminished? Let's understand that. So suppose we have a ray of light parallel to the principal axis, which is basically aimed at the point P. So what will happen to this ray of light after refraction? It will go like this. It will diverge as if it's coming from the focal point. So this ray, it would have gone to this point, we had there been no lens over here, but now it diverges as if it is coming from this point. And let's understand another ray which is aimed at the point B. What happens? That goes undimmed. Through the pole. So this ray is undimmed. So this virtual object B, its real image is formed over here. Its real image is formed over here. So this is my B prime. And if this distance was some y, in our calculation it came out to be how much we got? 100. So this y came out to be 100. So this is an example of a virtual diminished inverted image A prime B prime of a virtual object. Now, this kind of situation is not possible for a converging lens. In a converging lens, a virtual object always gives you a real image. But in case of diverging lens, a virtual object can also give you a virtual image. This is the ray diagram corresponding to it, and I'll show you the calculation corresponding to it above. Okay, so hope this case of virtual objects is clear. So what we can see in conclusion is that a virtual object can produce a real but diminished image. Sorry, real or magnified. Sorry, real diminished, virtual diminished, or virtual magnified. All three cases possible. So this will be real magnified. these are the cases. For a diverging lens. Okay, people, so hope this is clear to all of you. Now we move on to a couple of very simple applications of lens formula. The first of the two is two thin lenses in contact. We have a very simple calculation for this. Suppose we have, just for the sake of argument, example, I'm taking both the lenses to be convex, but they could be anything else. Any combination of two lenses. So this one is having a focal length f1. This one is having a focal length f2. And we want to understand equivalently how they behave. So we just throw light on them parallel to the principal axis and find out where the final image is. So that becomes the equivalent focal length for the combination. So suppose, like in my diagram, I'm assuming that this is a converging lens. So the light from this will give me my first image. Let's say I1 at the focal position of lens 1. This is my first image. This one is lens 1, this one is lens 2. Now that image I1, that becomes the object for lens 2. And suppose lens 2 now converges this light and the final image is produced somewhere here. So this becomes the image produced by the second lens. That becomes my final image. So that becomes my equivalent focal point. It's a very simple calculation. For the first lens, 1 by V1 minus 1 by infinity is equal to 1 by F1. Where, because the incident rays, they are parallel to principal axis. And the image I1, so we are putting V as. Now for the second lens, what does that mean? The object is I1. So the object distance should be V1. Because they are thin lenses, so they have a common pole. We won't consider any distance between the poles. And the image I2, that position we will put as equivalent focal length. So that's the final position of image. For incident rays which are coming from infinity. So that is the equivalent focal length. So 1 by V ke jagah 1 by F equivalent minus 1 by U ke jagah V1 is equal to 1 by F2. So for the second lens we have this one. So you can see two very simple equations, this one and this one. If we just add the two, you get rid of V1, you get the formula of the equivalent focal length, which becomes 1 by F1 plus 1 by F. Equation 1 plus equation 2 gives us a very simple equation that 1 upon F equivalent is equal to 1 by F1 plus 1 by F2, where F1 and F2 have to be substituted with proper algebraic sign. Cartesian sum. So before you write this down, another point is that power of a lens is defined as 1 upon focal length. So here we can also say that the equivalent power becomes power of the first lens plus power of the second lens. You should also know that unit of power is diopter, where 1 diopter is equal to 1 meter inverse. Alright, so this is a very simple formula to keep in mind. But remember, this is for thin lenses in contact. There should not be any gap between them. If there's a gap between them, then you have to solve it the way we solved the previous problem. So the combination of the two lenses can be replaced with an equivalent lens. Okay, so F equivalent is the focal length of an equivalent single thin lens. And use that single thin lens to replace the combination of the two. Okay, so this is like a very typical type of question at the JEE level based on this. So let's see an example. So in our next example, what we have is this kind of thing. We have so this is a thin concavo-convex glass lens. Refractive index 1.5 and radii, let's say 90 centimeters and 60 centimeters. Now what we are also doing is we are pouring a thin layer of water top of this over here. This is a thin layer of water which has refractive index 4/3. And it's in a vertical plane, so this will be a plane surface of water. Now, if we place a point source of light somewhere on the principal axis, at a distance x, because this is very thin, so it doesn't matter whether I'm taking x from the surface of water or from that surface, it doesn't matter. So we have to find x so that the rays of light emerge from this side, like this, parallel to the principal axis. So we have to find the value of x so that this happens. So this is the typical type of question where you use the combination of lenses and reduce this combination of two things, a water lens and a glass lens, into a single equivalent lens. And you can do the problem in a very easy time frame. Otherwise, solving it event by event will take too much time at the exam level. Just try out this question, people. Okay, anybody got the answer? You have to basically find the focal length of the combination. So what you do is you think of this combination as if you have this thing is equivalent to a water lens in contact with a separate glass lens. As if it's like that. That is equivalent to a single equivalent lens. So F equivalent is nikalna. Okay, let me verify that. Okay, so this is the concave convex glass lens with water layer. So this is equivalent to a concave convex glass lens in contact with a convex water lens in contact. That is equivalent to a single thing. Okay. So now let us understand the properties of each. So the glass lens like this side will have 90 centimeters, this side will have 60 centimeters. So 1 upon focal length of the glass lens, let's say, is 1.5 minus 1. 1 upon minus 90 minus 1 upon minus 60. That's 0.5 into 1 by 60 minus 1 by 90. That is 1 by 360. That's the power of the glass lens. That's the first thing. Now you think of the water lens. So mu is 4 by 3. This side is 90 centimeters. So it's in contact with that glass part, and this side is plane. So 1 upon focal length of the water lens is 4 by 3 minus 1. 1 by R1 minus 1 by R2. So 1 by 3 into 1 by 90. So 1 upon 2. That is the power of the water lens. So now water lens plus glass lens in contact, it is equivalent to a single thin lens which has focal length such that it is like this. So equivalent focal length is like this. Okay, so just go through this calculation and verify on the working also. R1 is assumed infinity because it's a plane surface. Water का जो ये vertical surface होगा, it will be a plane surface. Plane surface is always taken with radius tending to infinity. For example, when we had seen how to calculate focal length of a plano-convex lens. Understood, Aditya? Okay, good. Now let's see the calculation of the individual lenses first, then we'll come to the equivalent. Okay, people, so hope the values are correct. You can see that the water is in contact with the glass here, like this. If this is the glass, then this is the water. So this in between one is 90 centimeters. This one is 60 centimeters. And this one is a plane surface. So that's why when we are considering the water lens, we have 90 centimeters on one side and the plane lens on the other side. हाँ तो ठीक है ना, वही ले लो, क्या फर्क पड़ता है? So you get the same thing, no? So 1.33 minus 1 here will give you 0.33 into 1 by 90. So 0.33 is 1 by 3 only. Okay, 4 by 3 and 1.33 are one and the same thing. Only 1.33 is an approximate value of 4.4 by 3, because it's a recurring non-terminating decimal. If you take 1.1 by 1.3, it's a different thing. That's a big approximation. Utna difference तो आ जाएगा 270 और 300. This is a huge difference. 1.30 and 1.33. It's nearly a 3% difference. Anyway, the thing is, whatever you take in the method, so now you understood the equivalent focal length. Now, what will our final answer be? It will be equivalent focal length. So the distance x should be this much. So finally, in our question, the distance x at which we are keeping the point, so that should be equal to equivalent focal length. So that should be that approximately 154. So we keep this point source at a distance equal to the equivalent focal length, then light coming from it will emerge parallel to the principal axis. Alright, people. So hope this type of question is clear. You'll find plenty of questions, and especially JEE advanced type of exercises where you can use the application of this. Now the last thing in the lens and combination related formula. So thin lens in contact with a mirror. So let's say we have got some kind of lens and then we got some kind of mirror. And they are placed more or less in contact like this. So light which is incident like this will suffer refraction, reflection and refraction. And let's say finally, we get some, suppose the incident, the final emergent light comes back like this. So this will become the equivalent focal position. So we can say that this combination acts equivalent to a single mirror of focal length F equivalent. Okay. We can find out how much that F equivalent is, provided we know the focal length of the lens and we know the focal length of the mirror. If we know these two, then from that we can find out this. So just make a note of this, then we'll discuss what that formula is, and then we'll also learn how to do the applications as well as the derivation. Okay, so the formula is given by this, that 1 upon F equivalent is minus 2 upon focal length of the lens plus 1 upon focal length of the mirror, where things must be substituted with proper algebraic sign. Okay. And this also comes with Cartesian sign. So in this, let's first understand the application, then we'll come back to the derivation. So for example, suppose we have something like this now. we have a convex lens of focal length 60 centimeters, and it is suppose kept in contact with a convex mirror lens. This is convex mirror of radius, let us say, whatever, let's say 90 centimeters. And suppose we have a point object somewhere here, which is this y of 3 millimeters and x of, let us say, 90 centimeters. So this is a thin convex lens. Thickness does not matter. So we have to find the image position. So as you can see, solving this without the formula becomes very lengthy. We have to solve for refraction through the lens, then reflection by the mirror, then again refraction through the lens. But if we convert this to an equivalent system, then it becomes very easy. So let's solve it by that first, and then we'll show how to solve it by the other method also. So what we can do here is replace the combination of thin lens plus mirror in contact with an equivalent single mirror. And then solve the problem. Then solve using UV formula for mirror. This seems like the easiest thing to do here. So 1 upon f equivalent should be equal to minus 2 upon focal length of the lens plus 1 upon focal length of the mirror. Now the sign convention we'll use is that this side is negative, this side is positive. Light is coming from here. So the focal length of the lens will be plus 60 centimeters with proper sign convention. They told us that it's a converging lens with a convex lens of focal length 60 centimeters. With proper algebraic sign, it will be like this. And the mirror was a convex mirror. The center of curvature is here. The focal length of the focal position of the mirror is here. So this also has a focal length which is plus of 45. There is r by 2. Focal length of the mirror is plus 1. Okay. So this is what we will now substitute in the combination formula. Just give me a moment, guys. I'll shut this and just relaunch the program once it's getting hanged. Right, so this is what we should substitute in this formula. this equivalent formula. Substitute this. So we get now 1 upon f equivalent is minus 2 upon focal length of lens, which is plus 60, plus 1 upon focal length of mirror, which is plus 1. So this combination will act like an equivalent mirror, which is like this. So 1 upon f equivalent is 1 by 45 minus 1 by 50. That is 2 minus 3 by 90. So minus 1 by 90. So it will act like the equivalent mirror of focal length minus 90. So what kind of mirror has negative focal length? It is a concave mirror. The combination will act like a concave mirror of focal length 90 centimeters. Okay. So now this whole situation that we had, the object kept somewhere over here, this can be replaced with equivalent mirror, which has equivalent focal position. And I think we have taken the object distance as 90. Yeah. So we had actually taken the object at the focal. So you will see that we will get image at infinity in this case. If we had taken something else, it would have been something else. So this is the way of doing the question directly. Now we'll also see the second method where we can solve it one event at a time. But first note this down and understand the full application of sign convention and everything else. Yeah, actually, ray diagram I haven't come to because I haven't solved this by this method at all. Okay. Solved it by the UV method. If you were thinking what's happening in terms of the rays of light over here, the ray that comes from this point, after if refraction goes to the focus and you consider another ray present at the pole, what will happen is these two rays will become parallel to each other. So they will be infinite. That is how this point object O image is formed at infinity. Okay, now secondly, we can also understand this by fundamentals. So we are solving this by fundamentals. Then our method would be something like this. By series of events. How we solve that is you have this and this. We have an object kept here at x equal to 90 centimeters. With proper sign convention, this side negative, this side positive. The lens has focal length plus 60 and the mirror has focal length plus 40. So the first event the object is O. We'll take U as minus 90 centimeters. The lens has the focal length of plus 60 and the image is I1. So its position we want to find out. So 1 by V1 minus 1 by U is equal to 1 by plus 60. That's our first. We have 1 by V1 is equal to 1 by 60 minus 1 by 90. This will give us V1 as plus 1. Now this second event, उसके लिए क्या हो जाएगा? So what is happening here is that the rays of light coming from this, they are converging to a point behind. I won't get into the full detailed diagram, but suppose you take a point object here. These are emerging from here such that had the mirror not been there, they would have given me an image somewhere. So this image is now becoming a virtual object for the mirror. That's your second event. I1 becomes the object, in this case virtual, for the mirror. So we'll take U as V1 plus 180 and focal length as plus 45 and the image I2 which we want to find out. So 1 by V2 plus 1 by U, so plus 1 by 180 is equal to 1 by F. So 1 by F. So this will give us the second image. wherever that is formed. So V2 is equal to plus 60. So it is giving us a virtual image behind the mirror. So I'll explain that in the diagram. Just check my calculation also. Okay. So let's come back to the ray diagram and understand what's happening. So here what is happening is these rays, after reflection by the mirror, so I'm just showing by a different mistake, they will diverge even further. So they are giving you a virtual image I2B. And this is now at 60 centimeters. Whereas this I1 was at 180. So that virtual image actually becomes a real object for the lens. But now one thing very careful you have to be, for the lens, light is coming from this side. So for the second refraction by the lens, the focal point is here. Because light is coming from the other side. Okay, so that's what you have to understand now. So for the third event, which is the second refraction by the lens. So for our third event, which is the second time the lens is coming into play, I2 becomes a real object for the lens. Okay, because as far as the lens is concerned, the rays incident on it are coming like this. They are coming from this, albeit virtual point, but it's in front because so, and the focal position of the lens will be this time over here because it's a converging lens. So this is the focal point for the lens. It's a real focal point. We are using the same sign convention. This side negative, this side positive. So we will take U as plus 60. Okay. But we will take focal length of the lens as minus 60. Yeah, just a second. So where should the image be formed at infinity? So that's why now what will happen is that these rays will come out parallel to the principal axis. The image is formed at infinity. So 1 by B minus 1 by U is equal to 1 by F. This is the same result that we had got by just converting it into an equivalent system earlier. So this in a way is also showing us the derivation of that formula, how we are getting 1 upon f equivalent as minus 2 by focal length of the lens plus 1 upon focal length of the mirror. If you just repeat this process without taking values, and you take the initial position of the object instead of like 90 centimeters we are taking, you take it as infinity, then you will be able to derive this formula. So I'll just take you through each event again. Yes, the formula is valid for all combination of lens and mirror, including plane mirror also. Plane mirror, the radius infinity you will take. Right, and finally the third event. Yes. Okay, so this formula becomes a universal formula for combination of lens and mirror. For example, you can do another question yourself like this. Try it out by both methods and see what happens. So, for example, if I have this, a convex lens in contact with a plane mirror. Suppose this has a focal length of 60 centimeters. So what I can say by that formula is that it will act like an equivalent mirror of minus 2 by, now using my sign convention, this side positive, this side negative, plus 60 plus 1 upon infinity. Because plane mirror, its radius is tending to infinity. So focal length of the mirror will tend to infinity. So this will become minus 1 by 30. So that means it will act like an equivalent mirror of focal length minus 30. So it means that it will act like a concave mirror of focal length 30 centimeters. So that means that combination should act like this. Should act like this. The equivalent focal point here at 30 centimeters, which means that if light were to be incident parallel to the principal axis, it should converge here for the equivalent thing. So that means now you should also be able to prove by the same kind of method we did earlier, the 3-event method, that if light were incident like this, it will suffer refraction, reflection, and then again refraction, and come back here at the equivalent focal position, which should be 30 centimeters. You'll see that you try this out as a homework question. Show this by the distinct method, the events method also, and you get the same answer that we are getting by the equivalent focal length method. But obviously, once you're convinced of this and you're clear with this formula and its application, at the exam level, you can see that this is a one-line solution, whereas that will take a lot of time and can induce mistakes also. So this becomes a very important trick for these type of questions at the JEE advanced level. At mains level, you don't really have to bother about this, but for advanced level particularly, this becomes a very important formula. Okay. So with that, people, we come to a conclusion with today's lecture. So it's a very important lecture because the important problems we've done to do with virtual objects for both types of lenses. And then finally, the formula for the combination of lenses, equivalent power is equal to P1 plus P2, that formula. And this formula, equivalent combination of mirror and lens in contact, is extremely important for the more advanced type of questions. So make sure you revise today's lecture thoroughly, and now you can do maximum questions from previous year IIT papers and your exercises which are to do with the JEE advanced level. And you can discuss your doubts with me over the week. Now the next lecture will be mostly a problem solving type of lecture where we'll discuss many more examples of this. And we will also do some work with the last part of theory, which is dispersion of light by prisms. But that's just going to be half an hour or so. Most of the lecture is going to be about the application problems based on all this. Okay, so next lecture will be the final lecture of geometrical optics, and try to complete maximum problems and discuss with me before that. Okay? So that if there are any tricky problems, then I can discuss that during the lecture itself. So that's it from me, guys. Thank you. All the best and stay safe and stay well.